Um, okay, we're not talking about that. Get out of here. Um, so obviously this is just the input right I have right here. So the middle mouse button is for me to put down obstacles. This one is to set the source and destination. That all is not really important. What is the important part about this though, for sure, is let's see, three things really is just when you set an obstacle, each node, which is a single grid or cell that we were talking about earlier, you saw the squares, has sort of a few variables in it, right? We have whether or not it's an obstacle because it's blocked, right? We have world position and grid position. These are mainly just used to actually grab the cell so that we know where it is. Let's say if we wanted to get the cell from clicking our mouse, the way we would do that is we look at the what is it? We take our mouse position in world space and then snap it to the closest cell basically. And so in order to do that, we need the world position and also the grid position because it's what is it? The way we get from world position to grid position is to essentially an what is it? Algebra, right? You could just say because we know how big each cell is, we can divide each cell by, multiply each cell by the size of the cell and divide it, or was it? Divide it by 2 to get the half. Way important. Let me show that out because it's kind of confusing to demonstrate. Basically, if we have the x and y coordinate of this cell, we could say that we know where the middle or the world position of it is because we can divide it by the cell size, which is just sort of that, right? And then if we divide it by 2, we actually get that point in the center. Or divide the the cell by half the size of it. As weird as that sounds, that's just sort of how the algebra works out. And then of course, like I've said, we have our G cost, our F cost, and our H cost. It's actually cheaper that we don't store any of these values off start. Instead, we only put these values in when we are actually checking the neighbors of them. So that's why when you go in here, you're not having a list of cells or an entire grid already created for you. You're just propagating the cells you need to propagate. And so that's why I have this method here too, which is just the get F cost, because of course you don't want to necessarily get any of these costs unless you are choosing to traverse that node. And of course we have the constructor for it. This parent I'm going to explain later, but it comes in very very handy. So that was the grid renderer. Here's 2 things I made for us as well. Is this commented out version will get just the cardinal neighbors, and by cardinal I mean like north, south, and then west and east, right? And then there's intercardinal, which gets the northwest, south, and east, but also the northwest, northeast, southwest, southeast. And so that'll get you 8 cells. This one will only traverse cells. So you'll look at something like this. This is getting intercardinal directions as well as cardinal directions because we're able to traverse diagonally. Versus if we had just cardinal, we'd be traversing it like almost like Legos, right? You'd have to build up your ramp to it to get to the next cell, sort of like that. There's also another implementation of A-star that relies on something called Manhattan distance, which is a little bit different. It also sort of works in grids or like Legos like that. You have to traverse straight distances instead of diagonal distances. I believe that might be what you guys are using in the isometric project there.
Yeah, we're using the Manhattan distance.
Right, yeah. And there's no real right or wrong. I'm using something called Euclidean distance, which allows me to traverse things diagonally here. But again, it's like, what implementation do you want? And that's kind of how you have to decide. Taking a sip of water here. So this is actually how we get our cost, is this method right here, which will say basically, it's able to calculate whether or not it's going diagonal or not, or the distance, because it will say, and since it knows the, what is it? position of the cell. So you could do grid position minus grid position x. And so we're calculating this distance from the neighbor node minus the destination node. And whenever you subtract numbers in a vector, you sort of get a point or directional vector. Sorry. Let me explain that a bit better. So we have 2 points. When you subtract these points from each other, what you end up doing is drawing a line between the two. And that's just sort of the way that vectors work. And so that's exactly what we've done here, is when we have this neighbor node x position and subtract it from the grid position x of the destination, sorry. So when we're traversing from a neighbor node like this guy right here to the destination, we would look, let me make my pen a bit thicker. Destination node, neighbor node, and so basically we're drawing a line from there. And the way we can, and we end up taking the absolute value of that because we want an integer, which is what this is, just an unsigned integer. And essentially what we're saying is if x is greater than y, this is sort of the difficult part of the algebra. It's kind of difficult to wrap my head around, but basically what happens is we're going to set the y as the diagonal, and so that's why we were saying 14 there, because it's going to say, as I mentioned before, we have, whenever you're traversing diagonally, it gives the value of 14. It's a little too thick. Gets 14 versus if it's traversing vertically or in the cardinal direction, it'll do 10. And so the way it decides, or is able to figure out whether or not it's traversing cells diagonally or not, or whether the f cost should be mapped to be diagonal, is sort of this little logic right here. Now I can actually get into sort of the algorithm here. Basically, when we create it, we set up what's essentially just a 2D grid of nodes, or a 2D array of nodes. There's nothing special about it. You just say there's 2 for loops here, and it'll have our input numbers for how much we want, or how big of a grid we want. I have that right here. So our grid right here is only 20 by 20. Oh, now it's 0 by 20. Let's change that. 20 by 20. And so when we play it, it'll generate more squares. Let's see actually if I can do... Actually, no, because it's on start. Maybe this. User. This might create a lot of lag, but we'll see. We'll do it by... Copy this. That actually would be better. There we go. Okay. So if I play it and then change it in there, you'll see it gets bigger. Alright. So let's say if I make it 100 by 100, obviously can't really see that, but we can see, and we can obviously tell a lot bigger than before. And so very simply put, it's just the if I can go back to it, just creates the grid itself, right? Doesn't do any pathfinding, just sets up the play field, let's call it. And so A star is going to work on 2 things. We have an open list and a closed list. And then, of course, we have our actual path here that we're going to be returning later. So our open list is the nodes that we need to check. And so I can sort of show you that. Is our open nodes is basically our immediate neighbors. We're going to, if I can delete, there we go. All this annotations I made over here. So our open list is going to be our neighbors.
You're
so
muted.
Oh.
You muted yourself.
Thank you. Okay. So what was the last thing I said there? Let's see. I think was I talking about the size of this still?
Yeah, you were.
Okay. I'll restart that. What I was trying to say is that was just the constructor for the play space. Basically, is just how big do you need it, and we get those from the actual grid renderer, which I have serialized, which basically means just that we're inputting the values in the window over here as to how big we want this grid to be. And so what I was getting at was that it operates on three things. Our A star operates on three things. We have an open list, a closed list, and then an actual path that we'll be returning. And so the open list is essentially nodes that need to be checked. And so it'll check the nodes as they get added to the open list. Oh, I just did it again, muted myself. Let me make sure. Okay, good. And so we get the neighbors of this guy. There. Okay. So you get the neighbors, and then once we've checked this cell, we've got more neighbors because that's the best cell, and we're trying to continually choose the best cell to propagate. And so obviously in this case, we're going to be trying to traverse directly, and so we're going to be getting the neighbors of basically this cell. Let's do magenta, or I think it's more violet, but whatever. And so whenever we get the neighbors, we'll get. I'm also forgetting because we're intercardinal here. So this is actually what our grid will end up looking like. Is we have these cells which we've been choosing as the parents of these cells over here, because these are the cells where we have these are the cells that we're traversing. Sorry. And these are the neighbors of the cells that we're traversing, because every time we choose to calculate a new cell, we get the neighbors of it and propagate those neighbors with values. But it doesn't necessarily mean we choose all of them or have to go through all of them, because we can add the new neighbors to the front of the list. And so that's what we do. Every time we choose a cell, we add the neighbors to the front of the list, and we can also scroll through the list to find the best match, as far as when the values align, to show that we're going in the right direction, meaning that they have the lowest F cost or the lowest H cost.
What was that you said about the parent?
So the parent, right? I was going to get to that a little bit later, but I can sort of explain it. The parent is actually what we use because we had to. Let me explain it this way. If we were just checking cells at random, or not random, but if we were just checking cells and then saying, let's go ahead and propagate the cells and then put them in the closed list instead of having their parents linked, then we wouldn't be able to cleanly get a list as a path back afterwards. By giving them parents, we can say that the parents of the node, so this, if I can click on it, this guy is the parent of these three nodes, if I can click on it. But that changes because when we click this guy, now he's going to be the parent of these 8 nodes, basically. And so this guy is the parent of these 8 nodes. Let me copy this. So he's the parent of those 8 nodes. This guy's white right now because we don't know that he's the direction we want to go yet. Now this guy's the parent of these 8 nodes. Also, again, we don't know which direction we're going yet. And so you can see that we can trace, once we reach the end, all we have to do to find the path that we want to traverse is by scrolling back through the parents. Is because when we look from this, we're going to say this guy is the parent of this node, because the fact that he was the neighbor of these nodes. And I can sort of populate this cell over here. And as we know before, this guy is the parent of this guy. And so if we get to the destination eventually, all we have to say is, what is the parent of this node? It was this guy. What was the parent of this guy? It's this guy. And then this guy, and then so on until we get back to the source, right?
Okay.
And so that's how we generate our path, and also why we have this guy over here, this reverse, if I can find it. Let me just, real quick, do this. Retrace path. That's why we have this retrace path method right here, because that's what this guy does. Essentially, he goes back in and says, let me get this guy's parent, and we're going to reverse the list afterwards, because remember that since we're traversing it from back to front, it's going to be that it's going to look like the source is our destination, when really it's the source is our source and the destination is our destination. So that's why we have this reverse. And this is not something I built. This is a extension of the list variable in C#. And so essentially, what we get from that parent behavior is that we get to traverse backwards, very very cleanly. Because let's imagine that we didn't have that parent system, we would instead have to say, now that we've calculated all these nodes, now let's scroll through this big list of closed nodes, which I was pointing out up here. There we go, closed list. Instead, if we didn't have the parents, basically we'd have to like go through all the closed lists, find the best values, or even have some sort of marker on the cells. And so basically all it does is just make it, what is it? It makes it a linked list, but it's a linked list inside of another list, which makes it very interesting, let's say. And so it's weird, quite frankly. But it's very nice and conducive, obviously. It makes it a lot, it takes a lot less computational power to sort of actually compute. I mean, there we go. And so, as I was saying, we're going to start at our source, because we have our open list is the list of nodes we're checking, right? And so we're going to add our source, which is just our starting position. And then we're going to, when we have more than one node in our list that we want to check, we're going to do all of this. So basically we're starting out with here is we're saying the current node we're going to check is the first node in the open list. And that's always going to be true because as we're traversing through the nodes, we're going to be removing nodes from the beginning of the open list here. So immediately we can say, let's see, sorry. Right, okay. So we're just getting the actual costs themselves. This is actually not very efficient. I should have saved the cost, to be honest. I'm realizing now. But basically what we have is we're checking to get the best cost here. And then we're going to add sort of the... sorry, let me look at this. We're going to exchange the current node and remove them. Yeah, okay, sorry. I had to refamiliarize myself. Basically what happens here is we are trying to find the best node to traverse. So when we get the neighbors, we add them to the open list, right? We're like, we need to check all these guys. And then just before we do that though, we're checking what is the best one to be in the open list, and we're slowly removing nodes from the open list to be checked. Someone's screaming outside. And so if we also look at this, not that yet, actually. Right, okay. Yeah, so all this is just, once we reach the destination, we don't need to worry about any of this. Because we don't, or because we haven't reached the destination yet, we're only on the first node, we're obviously going to skip straight to this, which will get neighbors. And all neighbors is, I actually was looking online for some clean code to write for getting the neighbors, and this is actually probably the cleanest code I've seen in a very long time. Let me show you how this works. It's 3 fors and 1 if. And basically what it does is it has, let me write some text here too. It's going to start at -1, and then it's going to do an iteration, obviously plus plus. Let me do this as well. Come on. Get him over here. Second. And so it'll go through and get all these cells except this, except when it has this if here, which is x equals 0 and y equals 0, it won't get it. And so with just this little bit of code, we can get all the neighbors really nicely like that. And by the way, that continue statement, basically what a continue is it just says don't check for this, like, or don't do any iteration on this, go ahead and just skip to the next. It's like, you know how, I'm pretty sure most of us are familiar with break jump statements. This one, instead of breaking out of the loop, it's going to just say do the next iteration. So that's the way to think about that. And so that's the code behind getting the neighbors. Once we actually have the neighbors, we need to check if they're valid, right? And so we're going to say get the node or the position or grid position of the current node that we're traversing, and we're going to add that to this value up here. And so as we're checking nodes, let's say we're on the corner right here. We only have these 4 valid nodes. If I can put that over here. Because since we're on the corner, we don't actually have down here. Down here does not exist. So that's all this serves to do, is to check our corners, basically. And so I guess this as well. Hold on. When we have our good old friend, the giant if statement, check over, basically, is the position -1, because our lowest position we can have here is 0, right, because it's an array. Is it bigger than the position of the array? Is it exceeding the bounds over here? And then of course, does the actual node exist? There we go. Of course, then we can add that to the neighbor list and then return the neighbor list after we've iterated through that entire through the entire list of neighbors that we have or can possibly have. And then from that, we can actually go through each neighbor, check first of all, is it blocked, right? And is it already been checked off? Is it in the closed list? And then we can actually generate as well the gcost, or get, sorry, the, I believe this is fcost. I just didn't mark it. Let me change that. Because that's gcost plus distance cost, or get, oh, it's direction cost. Gotcha. Okay. So direction cost essentially is what this was the, whether it's diagonal or straight, or basically gets you an estimate on the cells that you would have to traverse, assuming a perfect world and you have no obstacles. And so you'd get the directional cost, which would be from, I believe, yeah, from your neighbor to your destination. So that would be, let me go back in here because I have my notes on this. Distance from the end node, which would be h cost. So yeah, h cost plus h cost plus g cost would be f cost. So let me real quick change that up for you guys when I release this. You guys can actually look at it properly. F cost. Let me do change something I don't want to change. Okay. Cool. There we go. Sorry about this. Okay. So now that's all properly labeled. We have our f cost essentially, and we can do what is this? I'm lost now. So we have we're adding to the open list if it's not already in the open list, right? And then we have our h cost is getting directional cost. And then, but we're doing that, right? Close current node. Okay, right. So we're just traversing the different nodes here. Sorry. Because what we're doing is we're saying, let's get the different costs and let's actually insert them in our neighbors here. And so this is how we propagate our neighbors full of values. So we're not just drawing blanks. We're actually putting the values in here. Like we said, this was like 74, and this was, I think it was 84 or 64 or something like that. Anyway, you get the point. Actually puts the values into the cells so we can check across them. And also, of course, if they're already in the open list, then we don't necessarily need to add them. And so that's what this little not in the open list is for. That was a lot all at once. I'm hoping we can have some questions. Obviously, I will say, in here, some nice things for you guys. There's this text file, which I've included, which has a lot of the resources I personally used. Let's see. Sebastian log, always amazing. Then we actually have sort of the pseudocode for it as well here, which you can sort of see. Basically, the open and closed list, right? We had the loop, which is going to check all of our, it's going to find the lowest F cost, and then it's going to remove it, as well as also get the neighbors, and then set the neighbors, right? And that's sort of what we all just went through. I'm trying to think of what else to explain, or how better to explain it. Because that is essentially what happens, is this entire program essentially will get the neighbors, and then traverse, get the best cost, and then traverse back to the beginning using the parent nodes it established along the way. And sort of that's the implementation. I'll send this out as well, and you guys can ask sort of. I know I mentioned was it H cost and G cost and F cost a lot, which is certainly going to throw some confusion around. So if you have questions about that, feel free to ask. Another thing that you might have questions about is Euclidean distance versus Manhattan distance, and we can go ahead and explore that for a minute.
Yep.
Let's see. That was not what I wanted. Yeah. I'm just sort of filling the void right now, so like I said, if you have questions, I'm not presenting anymore. I'm just trying to get logged in here so I can share the actual project with you guys, so you guys can look it over.
I did actually want to ask, so with the code we were using for this demonstration, I was wondering how it would work if, say, like, one of the tiles that was on the path ended up having two parents. I don't know if that's possible or not, and like how that would work with the rest of the
So I understand what you're saying. So, but the nice thing is, because of the way this works, let me show you. So it has a variable that it gets assigned as parent. So it can only ever have one parent, which is the nice thing. But what I might be able to clarify is that the fact that this parent does get overridden.
Okay.
So what you can have is, let's say instead we started somewhere from the. Do you want to start from the middle? Let me think of how to best demonstrate this. Let's actually no. I feel like the best way is to add in some blockers, because that's usually when it happens. When you have blockers and you're not just traversing straight to the end way here. That's fine. Okay. So, let's say we have some blocks here. Obviously, we know that this is going to be the parent of this, and this, and this. The thing is, once we get to here, we're going to get, this is the parent of all of these 8 cells, but then we're going to make this new one, which is going to become the parent of all of these, I believe it's going to be 5 cells. And so, as we continue walking around, this guy is still the parent of this guy, and we can avoid resetting this guy. Sorry, let me real quick just do this. So you'd assume that once we check this guy, that this guy over here would get, or this cell would be overwritten as the parent. So it would say, oh, this guy's my parent now. Or sorry. That's actually the correct implementation. Whoops. Hold on. Yeah, because basically it would be traversing. I'm trying to think of a situation where you'd get to, or you'd have, let me think. So this guy becomes the parent of these 3 guys. Then this guy becomes parent.
The tile above the blockers, because that one should be a parent of the 2 to the left, right? Or it's a child of the 2 to the left, rather.
Yes, there you go. Actually, thank you. And so this would. No, actually, this would be a child at first, because it would say that this around here is. Let me take a sort of vertical snapshot. Originally, it would say that these. Oh, let me click on the right thing for once. Here, get rid of that.
All right.
There we go. Okay, so we can just look at this for a minute. Originally, we would say that this tile, I can mark. Let me mark these in some different colors, so I can be like the blue tile, the red tile. So we have the blue tile, which is, let's say, that's our start there, right? And so these guys are just going to be child nodes at first. Then we're going to propagate this node. Let's say this. And now this guy is the parent of all of these cells, except for this guy, because what we do in code is we have, we're only checking the open list, and since we've already checked this node from this guy down here, it's going to say this guy is now in the closed list, and so we can't alter this necessarily, or we're not going to be bothering to alter this anymore, because we have, again, those two lists. We have the open list, let me find the open list, and then the closed list. And of course the open list gets, let me see actually where we get our open list from. I can sort of explain that. Let me get open list, come on. It's here somewhere, I swear. Open list index. I mean, obviously we propagate it somewhere. I'm just trying to figure out where the heck we do that from. Let's see. Okay, here we go. So this is our whole neighbor thing. So we're gonna check if it's already in the open list. If it's not in the open list, then we add it. But then there should be a check for closed list somewhere in here. Maybe it's in get neighbors. No. Let me see. Alright, so we have open list, open list, open list. Oh, or maybe that's the thing. When are we changing the closed list? Sorry. Let me do this real quick. Oh, no, we do that. We do that, actually. It's just up here. I missed that. So, yeah. When it's in the closed list already, what we do is we just skip it, basically. And so that's what we do, is whenever we traverse a node and decide that's the node we want to go with, then we close it, essentially. So this down here would be closed. Once we've traversed this and we're going up to here, this guy is now closed, and thus this guy doesn't get changed, but these guys are still in the open list, so they would get changed, if that makes sense. And of course, as we move to here, this guy would become closed list, because we were going with him, and then we got, of course, this guy, and then all of his surrounding nodes. I can sort of jankily add them in. So hopefully that's not making sense. Sorry to dig through the code for a second. Okay, and let me actually share this with you guys. Just gonna, the weekly doxing I put myself on, I mean, I guess if you guys want to email me, there's my email. Let's see. Oh, there's everything. Okay. Easter Pathfinding. Let me make this open, and then I can share it with you guys as well, so you can download it or not download it. Either or. Collaborators. Manage. Change visibility. Change public. Yup, I know. I've done this a lot. Let's do it. And then, if I can, I think I should just be able to share this link, and that should give you guys access here. Let me put that workshop code for you. And so, then there is one, I will say, the thing I was not able to get to that I was really sad about is because we're traversing this, let me just show you. Hello? Console? Did I break something? I might have to do some undos. Yeah, hold on.
Yeah, broken.
I think did I do anything else? Is it in here? Oh yeah, that might have done it actually, because I'm making a new thing every... Yeah, that would definitely do it. Okay. Sweet. There we go. Okay. So if I block this guy off, you'll see he can still reach inside there, even though obviously he shouldn't be able to.
Yeah.
And so that's something as well, is if you're traversing, let's do this, a grid like this, you're going to have to do an extra layer of, what is it, processing on the path that you have to make sure that these two aren't blocked. Assuming your movement would work like that. Obviously, I guess it depends on the game you're making, but I think for most of us, we wouldn't want to be able to phase through the concrete wall here. So, yeah. Other than that, you could just pretend you're using Microsoft Excel, or not Excel, MS Paint. Yeah. But no, it's kind of fun to just. Oh, that was actually a nice little look at that. I mean, except for that. But anyway, you get the point. This is kind of just a fun tool to mess around with, even if you guys don't even want to necessarily implement it in your game. The nice thing as well is obviously you guys can just throw this in your game. I don't really care if this is something you need for your game or something like that. There's I have linked in here, like I was saying, Sebastian Log. He's sort of the main resource I use for a lot of the things I've done, because he's just such a great. I mean, you have to see his channel. Let me see if I can. Oh, he doesn't have it linked on here. I'm joking. Okay, hold on. Let me link him because he deserves all the credit, man. I do seriously recommend checking him out, even if it's not for A-Star Pathfinding, because he has a lot of cool things. I think Stetson knows exactly what I'm talking about because I've shouted at him to watch it as well.
I do.
See, Sebastian Log. Yeah. Yes. And so yeah, he recently did a thing on ray tracing as well, which was kind of fun. He has. Let's do A-Star, and then I can actually link that as well. Yes, this. This in here. So, I mean, you can even hear him explain the theory if you really wanted to. But he has a lot of things. He even goes into how to make, first of all, optimization. He actually adds in the units and threading, or makes it multi-threaded for you. He does like pathfinding weights. Let's say you're moving across like sand or dirt and you prefer dirt for whatever reason. You can make it so that the cells try to, the pathfinding prefers to walk on dirt or something like that, but it allows it to walk on sand still. It's kind of fun things like that. So it also looks like he's got smooth weights, as in he has like a heat map almost. So yeah, I definitely recommend checking him out if you're more interested in this topic. Otherwise, I think I'm going to let you guys go or ask questions, either or. Yeah, also, if you want to stay and talk about your project or something.
I think I'm good. Thank you for the
Right. Yeah, thank you all for coming as well.